In the last step, we instantiated our two discriminators and our two generators, one for classifying or generating images from the X and Y domains. The next step is to define our loss functions and optimizers for training. As before, we'll want to define real and fake losses that look at the outputs of our discriminators and see how close the losses are to being real, 1, or fake, 0. And we'll also need to define a new kind of loss, cycle consistency loss. This loss looks at the reconstruction error between an input, say x, and a processed x, x hat, that's gone through our two generators, gx to y and gy to x, which here is referred to as f. In theory, going through these generators in a cycle will create an x hat that's the same as the original x. Any error is measured as the absolute value difference between x hat and x. Okay, so this is a completely new loss type. The second new loss detail is that in this case, we'll actually be using a least squares loss function for the discriminator, as opposed to cross-entropy loss. This approach is motivated by recent research. Basically, in an unsupervised approach like this, researchers observed that cross-entropy loss led to a vanishing gradient problem, and a least squares loss function instead was able to generate higher quality images and was a bit more stable during training. This structure is also referred to as a least squares GAN or LS GAN, and you can read the original paper on this approach at this link. What this means in practice is that you'll define a real loss and fake loss function that takes in our discriminator output and computes a squared loss term between that output and the desired label 1 or 0. For example, for our discriminator dx, I might pass in a real image x from our training data and I'll get some output. Then I can essentially calculate a real error as a mean squared loss by squaring the difference between that output and a real label 1. In Python code, these two asterisks mean raised to a power of 2. So I'm taking the squared difference of the output and the label 1, and then I'm taking the mean of all of these values. So this is a mean squared loss, and I can do something really similar for a fake image, only instead of comparing the output to the value 1, I'm going to compare it to the value 0, and just end up squaring the output term. Okay, so in this cell, I want you to try defining these three loss functions. The first two take in the outputs from our discriminator. The real loss function should compute a mean squared error between this output and real labels, and the fake function should do the same thing but with fake labels. Lastly, I have a weight function that will take in a real image, its reconstruction, and a lambda weight. This is our cycle consistency loss function, and it should do two things. First, it will calculate the reconstruction loss, so the absolute value difference between these two inputs, the real image and its reconstruction. These are going to be pixel-wise differences, and so you can take the mean of the absolute value difference here. Then it should multiply that loss term by the passed-in weight value here. If you recall from Junyan's videos, the lambda weight basically tells us how weighty or how important the cycle consistency loss term is. Okay, then there's one more thing we have to do to complete our optimization strategy, and that's define atom optimizers for our discriminators and generators. In this case, I want you to create 3 different optimizers, one for each of our discriminators, x and y, and a third attached to the parameters from both of our generators, and I'm getting those parameters by adding them up as lists in this line. There are other ways to do this, but I think this leads to a nice solution. So your job will be to define the hyperparameters here by looking at existing papers or other resources that you find. Try completing the loss functions above and filling in these hyperparameters, and next I'll show you one solution.